Hi, welcome back to educator.com. Today we're going to talk about horizontal asymptotes. In the previous lesson we learned about the idea of a vertical asymptote, a horizontal location where the function blows out to infinity, either up or down. Symbolically we can express this as a vertical asymptote as x approaches some a, some horizontal location a, and when that happens f of x goes to positive or negative infinity. We can flip this idea to the reverse and discuss the idea of a horizontal asymptote. A vertical location which is approached as the horizontal location slides to infinity. As our x becomes very, very large, what vertical height do we go to? Symbolically, we can express it as x goes to positive or negative infinity, as in x becomes very, very large, either positive or negative, and f of x goes to some b, goes to some specific height y equals b. To understand this, let's take a look at our old friend from last time, our fundamental function 1 over x. Notice that as x grows large, we see f of x shrink down very small, right? As we go far out, we become very, very small. We can see we're at 1/10 over here and negative 1/10 over here. We can expand this to an even larger viewing window, and we can get a sense for just how small f of x eventually becomes. With our y going only from negative 0.5 to positive 0.5, we can see that by the time we've made it to 100, we're at these tiny numbers, right? We're at 100th and negative 100th respectively. So we see that it becomes really, really, really small given enough time. So the farther we go out, this f of x is going to sort of crush down to 0. We can see this behavior of being sucked towards a certain height in many rational functions. In 5x divided by x minus 2, we see it has this horizontal asymptote at 5. It sort of gets pulled towards a height of 5 in the long run. Over here with g of x equals negative 3x squared plus 6 over x squared plus 1, it gets pulled towards a height of positive 3. In fact, it gets pulled really, really quickly. Just like we had with vertical asymptotes where it never quite touches the asymptote, with the horizontal asymptote, it will not quite actually get to there. It's going to get very, very close to it, and we'll see that as we explore why this is occurring in just a few moments. So we'll formally define this behavior in a little bit, and we'll name it. We'll name it a horizontal asymptote. But first, let's understand why it occurs. What's actually making this happen? So let's start by investigating f of x equals 1 over x. Since x is in the denominator, as it grows really, really, really large, this giant denominator crushes the numerator, right? The numerator just stays still. It just stays at 1. But the denominator gets big, right? It has x, and so it's able to march out forever. So as it gets really, really big, it crushes the numerator down to 0 in the long run. So if we look at the negative side, over here's negative. So we've got our vertical asymptote at 0, and we're looking at what happens as it slides to the left. We have negative 0.5, and it's at negative 2. Negative 1, then negative 1. But as the numbers get larger and larger, negative 5, we're at negative 0.2, negative 10, we're at negative 0.1. Negative 1,000, we've made it to negative 0.001, and it's going to just keep getting smaller and smaller and smaller. Negative 1 billion will be a very, very tiny number. Now notice that there's no number we could plug in to actually get 0. We're just going to get very, very small numbers. So these giant denominators are going to make very, very small numbers that will approach 0. We won't actually make it to 0, but we'll get really, really, really close to it. Same thing happens on the positive side. If we look what happens as we go positive, we start sort of looking from our 0 and we go to the right. 0.5, we're at 2, at 1, we're at 1, 5, 0.2, and so on. We get at 1,000, we're at 0.001, and as we get really, really large numbers, we'll get crushed smaller and smaller and smaller. Since the denominator grows so much faster than the numerator, right? The numerator isn't moving at all, so it's not even growing at all. The fraction will eventually shrink to 0, as we've got very large denominators crushing our numerator. For any rational function, if the denominator's degree is greater than the numerator's degree, that is, if the denominator is able to grow faster than the numerator is able to grow, the rational function will eventually go to 0, right? If we've got x squared over x cubed plus 5, that's eventually going to get crushed down to 0 because x squared doesn't grow as fast as x cubed plus 5. So the x cubed plus 5 can effectively outrun x squared in the long run, so it will get much larger than x squared will, and so it will crush the whole thing down to 0. So if the degree is greater in the denominator, right, 3 versus the numerator's degree, 2, it will eventually get crushed to 0. How do we get rational functions with a horizontal asymptote that isn't at 0 then? So let's look at one. F of x equals 5x over x minus 2. And of the two graphs that we saw, that was the one on the left, the red one that had a horizontal asymptote at 5. So if we plug in 1, once again, this will be the negative side, what happens is we go more and more negative. If we plug in -1, we'll get 5 over -1 minus, if we plug in +1, we'll get 5 times 1 over 1 minus 2, so we get 5 over -1, which is -5. If we plug in -10, we'll get -50 over -12, approximately 4.17. -100, -500 over -102, approximately 4.90, -1000, -5000 over -1002, 4.99 approximately. So notice, as we plug in these things, the 5x here and the positive x here, they wind up growing at the same rate other than this factor, this multiplicative factor of 5. So the top grows 5 times faster, but precisely 5 times faster than the bottom is. So as they go out one way or the other, they're going to wind up approaching the top growing at 5 times faster than the bottom growing, so it's going to wind up approaching 5, because when we have very, very large numbers that we're going to put in, eventually like 1 million, it'll be 5 times really big number divided by really big number, so they'll cancel out to 5. We've got this other factor of the -2 here, but as the numbers get much, much larger, like 1 million minus 2, 1 million hardly notices the -2, right? It has a slight effect, but it's not much of an effect, and so as we get down to farther and farther values out, as we get to larger and larger values, it will have less and less of a relative effect, and we're going to get closer and closer to 5. Exact same thing happens if we look at what happens on the positive side. If we start off by plugging in 3, we're at 15 over 1, so we're very different at 3, we're at 15. But we plug in 10, we're 50 over 8, 100, 500 over 98, 1000, 5000 over 998. We've got this difference that's, becomes less and less impressive. This -2 becomes less and less meaningful and eventually becomes 5 times number divided by number, which goes to 5. So look at how close we've managed to make it by the time we're at 1000. And this pattern will just get far closer and closer to 5. As we continue this pattern out, we'll just get much closer to 5. Once again, we'll never touch 5 because we'll always be off by this factor of -2. We'll always be slightly imperfectly equal to 5, so it won't ever actually equal that horizontal asymptote precisely, but it's going to get arbitrarily close to it. It's going to get really, really, really close until we're now dealing with numbers like 5.00000001, right? And so on and so on. We'll be able to get to any arbitrary closeness we want as long as we look at x large enough. Once we get far enough from the vertical asymptote at x equals 2, we see that the numerator and denominator grow at a constant ratio, 5x and x. So for any rational function, if the degrees of the numerator and the denominator are equal, we will get a horizontal asymptote that isn't equal to 0. We'll get a horizontal asymptote at some height. So notice, the 5x here and the x here, they both have the same degree, a degree of 1. So since they've got the same degree on the top and the bottom, they're growing at the same rate. In a way, other than that multiplicative factor of 5, they're running in sort of the same scale of growth. So since they have the same scale of growth, they're going to grow around the same rate, which means it's only that multiplicative factor that's going to determine the height that it ends up at. A horizontal asymptote is a horizontal line y equals b, whereas x becomes very large, plus or negative, f of x gets arbitrarily close to negative. Symbolically, f of x gets arbitrarily close to b, not to negative. So symbolically, we show this as x goes to negative infinity or x goes to positive infinity means that f of x will go to b. We're going to get to this height. We're going to move towards this height surely, steadily. It might not get perfectly to b. In fact, it almost certainly won't, as what we were just talking about, but it will get really, really close to b. It'll get arbitrarily close to it. Informally, we can think of a horizontal asymptote as a vertical height that the function is pulled towards as it moves very far left or right. Over the long term, it will start off somewhere else, but it sort of gets pulled in the long term to a certain height until it gets really, really close to this horizontal asymptote. We can take this idea and go beyond just having a horizontal asymptote. Consider f of x equals x cubed minus 1 divided by x squared. As x gets large, we see f of x grow very close to the line y equals x. We can see that on that dashed orange line going through the y equals x line. We see how close it becomes. In fact, it grows so close so quickly that we almost can't tell the difference between the two on the far parts in this graph. They'll never be perfectly the same because we've got this -1 here, but we'll become really, really close to it. This idea is similar to a horizontal asymptote, but it's no longer horizontal, right? Since it's at a slant, we can't call it a horizontal asymptote, so instead we call it a slant asymptote. Sometimes it's also called an oblique asymptote. So what's going on? Why do we see this? Once again, we're trying to consider what happens to the function in the long run. The idea of all this horizontal asymptote, slant asymptote stuff, it's a question of what happens to this function as we look at very large x, as we go really far right, as we go really far left. In this case, we could plug in large numbers to see what happens, but that'll slightly obscure some details for other slant asymptotes. So instead, what we want to notice is that we can rewrite the function. So if we've got x cubed minus 1 over x squared, we can go, oh, hey, look, we can divide out the x cubed, and we can break our fraction apart so we get x cubed over x squared minus 1 over x squared. And so the x cubed and x squared cancel down to just x minus 1 over x squared. So by using division, we can see that this function in a new way. In this form, it's clear that as x goes to positive or negative infinity, this part right here, since it's 1 over x squared, that's just going to sort of get crushed down to 0 by its much larger denominator. But the x here will wind up just continue plugging on. It'll just keep moving forward. So in the long run, as we get to very large x, this part here goes to 0, but x continues going out, so effectively, the function will become just x. We can also get this x cubed minus 1 over x squared. We can break it into this format through the process of polynomial long division, which will be necessary when we've got slightly more complicated denominators we're dealing with. So you write this as this plus, minus 1. So in that way, we'd have x squared. How many times does x squared go into x cubed? It goes in just x. X times x squared gets us x cubed. We have nothing else, so we subtract by x cubed. That gets us 0. We bring everything down. And so we've got 0x squared plus 0x minus 1, which leaves us with just a remainder of negative 1. So we've got this remainder of negative 1. So x cubed minus 1 over x squared is equal to x plus the remainder. So the remainder is negative 1. And then we put it back over our original denominator, the thing that we divided by, right? So we get x plus negative 1 over x squared, which is the exact same thing that we had down here on this line. So we can get this through polynomial division, which will be necessary when we're dealing with slightly more complicated denominators. So we can also define a slant asymptote similar to how we defined a horizontal one. It's also called an oblique asymptote sometimes. A slant asymptote is a line y equals mx plus b. Remember, mx plus b, just our normal slope-intercept form for a line. Whereas x becomes very large, positive or negative, f of x gets arbitrarily close to that line, y equals mx plus b. Symbolically, we can show this as x approaches negative infinity, very large negative values, or x approaches positive infinity, very large positive values. F of x will go to mx plus b. F of x will approach just being the same as this line, mx plus b. Informally, a slant asymptote is a non-horizontal line that the function is pulled towards as it moves very far to the left or to the right. So we might start off at different heights, but as we get to farther and farther x, we wind up getting pulled along this line, getting pulled along this slant asymptote. We can even go beyond the idea of a slant asymptote. Really, the question we've been working on can be phrased as, what does the function look like in the long term? What is the long-term behavior of this function? So far, we've answered that with horizontal and slant asymptotes. But a function could also tend to a curve. It can tend to anything, really. If we had x to the fourth plus 17x plus 20 over 10x squared minus 10x minus 20, well, notice, we could make that as squared and to the fourth up here. So the degree of the top is 2 steps larger than the degree on the bottom. That means that over time, it's going to effectively be the same as x squared coming out of that. This sort of x squared, x to the fourth divided by x squared. We're going to get something that looks kind of like an x squared, which is a parabola, which is exactly what we see here. As we get to very large x values, we see it get pulled along this curve. Notice this curve that we've got of a parabola through here. Now, it will behave differently when we're at the vertical asymptotes, because we've got vertical asymptotes x minus 2, x plus 1. So vertical asymptotes at negative 1 and vertical asymptotes at positive 2. So it will get pulled into these vertical asymptotes in various ways. But in the long run, as it gets to very large x values, it gets pulled into this parabolic shape. In fact, if we were to divide this out through divide the bottom into the top, through polynomial division, we'd be able to find that it eventually is approaching the parabola 1/10 times x squared plus x plus 3, and that's why we see that parabolic curve right there. Pretty cool. That said, we're not going to really see this in this course, or probably in any other course that you're taking right now. While this shows us an interesting idea, don't expect to see this in a normal class. Few textbooks and very few teachers will discuss anything beyond the idea of a slant asymptote. As such, we won't be exploring the idea any further in this class either. However, it's useful to notice how all these ideas have been linked. They're about answering, where does this go in the long term? What is happening eventually to my function? How will it behave when I look at very large values being plugged in? We can get a sense of this by thinking about what happens to the function as the numbers get larger and larger and larger. What will happen? What general way will this function behave in when we're plugging in x that's a million, a billion, a trillion, really, really big x? That's what all these ideas in this lesson have been about. What happens as x becomes very, very large? How does this thing behave? It could behave in these non-slant asymptote things where it pulls into a parabola or some other polynomial shape, but we're going to restrict ourselves to just horizontal and slant asymptotes since that's what most other courses look at, and they're also the easiest for us to approach right now. Horizontal slant asymptotes and graphs, just like their vertical cousins, it's customary to show horizontal and slash asymptotes with a dashed line. So we normally use a dashed line to show, hey look, here is an asymptote. So if we had 4x to the fourth plus 3x cubed plus 10x squared divided by 2x to the fourth plus 1, we'd get this graph over here on the right. And notice it's got a horizontal asymptote at 2. And so over the long run, our graph gets pulled towards this. Now notice that in the middle, it has a behavior that's totally different, right? It has this interesting behavior in the middle. So unlike vertical asymptotes, the graph can cross the horizontal asymptote. It's allowed to actually cross over that horizontal or slant asymptote. Furthermore, there's only ever one horizontal or slant asymptote. You can't have multiple horizontal slant asymptotes the same way you can't have a vertical asymptote. In any case, over the long run, the graph will be pulled along the asymptote. That's the idea of an asymptote to really get across, is that an asymptote is about the function eventually being pulled along it, or if it's a vertical asymptote, being stretched up along it vertically. How to find horizontal and slant asymptotes. A horizontal or slant asymptote tells us how a function behaves in the long run. That's the idea here. It's fairly easy to determine if a function has a horizontal asymptote, and if so, what it is. We'll see a method for that first. Finding a slant asymptote is a little bit trickier though, and we'll look at its method second, but it's not that difficult. Any rational function is in the form n of x over d of x, where they're both polynomials. So we can expand these polynomials into their normal form, right? Our blank times x to the n plus blank times x to the n minus 1 plus blank times x to the n minus 2, all the way until we eventually hit a constant. And the bottom one will be the same thing, right? Some other blank, so an will be the blank on the top, bm will be the blank on the bottom. And we have two different things. So n will be the numerator's degree, and m will illustrate the denominator's degree. There's going to be three possibilities. First, if n is less than m, then there is a horizontal asymptote at y equals 0. Why is that the case? Well, if n is less than m, then that means we've got a big denominator compared to the numerator, right? The numerator will have a smaller degree, so it's going to grow slower, which means that the bottom one will eventually grow large enough to crush the numerator. So we're going to crush it down to y equals 0. So if we've got a numerator degree, if the degree of the numerator is less than the degree of the denominator will eventually grow large enough to crush the whole fraction down to 0. If n is equal to m, if they're the same degree, so if we've got same degree, then what we're going to see is we'll see a horizontal asymptote that's based on the ratio of the leading coefficients. So we'll get a horizontal asymptote, but it will no longer be set at y equals 0. Since xn and xm are basically the things that in the long run are really going to determine how these polynomials are, and n equals m, then ultimately it's going to be an xn over bm xm in the long run, since xn and xm, well, they're both the same value. Since those things are at the front, they're going to really determine how the polynomial works in the long run. And they'll just cancel each other out, right? Because we'll have an xn over b, and I'll call it n as well, since we've got n equal to m, xn. Well, in the long run, what's effectively going to happen is we'll see these two things cancel each other, and we'll be left with just the leading coefficients, the ratio of the leading coefficients. That will determine what the horizontal asymptote is going to go to, is this ratio of what's the leading coefficient on the top divided by the leading coefficient on the bottom. What's our first coefficient here, first coefficient there. Finally, if n is greater than m, if we've got the numerator degree is bigger then there's no horizontal asymptote because the numerator is able to run faster than the denominator, and so it's able to escape the clutches of the denominator and actually keep going on to growing forever and getting less and less. Depends on how it's set up specifically, but we'll be able to have freedom on both the right and the left side as it manages to have very large values because it will be able to outrun the denominator because it's got a larger degree. All right, so let's talk about how to find slant asymptotes. A rational function has a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. So in the terms we were using before, where n was the numerator's degree and m was the denominator's degree, it'd be n equals m plus 1. We can find the asymptote through polynomial division. For example, if we have 3x cubed minus 2x squared plus 7x plus 8 over x squared minus 3x, we see, oh hey look, there's a 2 on the denominator, there's a 3 on the numerator, and 3 is equal to 2 plus 1, right? The same thing as what's going on up here. So we are 1 greater in the degree of the numerator, exactly 1 greater in the degree of the numerator than we are in the denominator. So we're going to have a slant asymptote. So at that point we use polynomial division. So let's see how polynomial division would work here. We have x squared minus 3x is dividing in. So x squared minus 3x dividing into what's in our numerator, 3x cubed minus 2x squared plus 7x plus 8. So how many times does x squared go into 3x cubed? It's going to go in 3x. 3x times 3x squared gets us 3x cubed, so yep, we were right. 3x times negative 3x gets us minus 9x squared. Then we subtract this whole thing, so let's distribute that negative minus 3x cubed. That becomes plus 9x squared. So 3x cubed minus 3x cubed is 0. Negative 2x squared plus 9x squared is positive 7x squared. Next step, bring down the 7x. So plus 7x. How many times does x squared go into 7x squared? Goes in plus 7 times, so 7x squared. That checks out. 7 times negative 3 minus 21x. We subtract that whole thing, so distribute our negative, minus, plus. 7x squared minus 7x squared, 0. 7x plus 21x, 28x. Bring down the 8. So we get plus 8 here. At this point, we see 28x. How many times can x squared go into 28x? Can't go in anymore because of our degrees. So we've got a remainder of 28x plus 8. And so notice how these are the same thing. 3x plus 7 is what we got as the result, 3x plus 7 here. And then plus our remainder, 28x plus 8, our remainder, 28x plus 8, divided by what we started off doing our division with. So that's how we get polynomial division, and indeed 3x plus 7 plus quantity 28x plus 8 divided by x squared minus 3x is what our initial rational function is equal to. So we can break it down. Break the function into two parts, a portion with no denominator. So the portion with no denominator is 3x plus 7, right? It doesn't have a denominator. So that is what our slant asymptote is, because 3x plus 7, well, 3x plus 7 describes a line, right? That is in the form mx plus b. So 3x plus 7, that's a line. And the remainder of the division, our remainder to our division, is our 28x plus 8, so that's the remainder to the division, goes over the denominator, x squared minus 3x, back over the denominator that we started with. And notice, 28x plus 8 divided by x squared minus 3x, because it's the remainder is always going to have a degree less than what we started off dividing with. So we've got 28x to the 1 divided by x squared minus 3x. So we've got a bigger degree on the bottom than we do on the top. So in the long run, the denominator is going to crush the numerator, and this whole thing will go to 0, and we'll be left with just 3x plus 7. So in the long run, we'll wind up having the portion that has no denominator and the portion that has a denominator, because the degree on the bottom is now less after polynomial division, it will go to 0 in the long term. Now, this method of polynomial division will also work to find horizontal asymptotes. So you can also use this method if you want to find the horizontal asymptote. It's just instead of getting a line here, you'll just get a constant. It'll just be a constant value if it's a horizontal asymptote as opposed to a slant asymptote. So you can also use polynomial division to find horizontal asymptotes, but we had that other method for finding horizontal asymptotes that was pretty fast, so it's normally easiest to just use polynomial division when you want slant asymptotes. All right, let's go over some examples. F of x equals 10x to the fifth plus 3x to the fourth plus 8x squared minus 2 over 2x to the fifth plus 27x cubed plus 12x. Is there a horizontal or a slant asymptote? So what we do is we compare the degree on the top to the degree on the bottom. They're the same degree, so if they're the same degree, we've got a horizontal asymptote. So we are a horizontal asymptote. Now, if we want to figure out what the horizontal asymptote is, well, we'll figure that out. And we just look at, so it's ratio of leading coefficients. What is the leading coefficient for the top and the bottom? The top has a leading coefficient of 10. The bottom has a leading coefficient of 2. We simplify that and we get 5. So 5 is what our horizontal asymptote will be. So y equals 5 is the horizontal asymptote. Great. So once we see that the degree on the top and the degree on the bottom are the same, we know we've got a horizontal asymptote that's not just going to be a 0. And now we figure it out by looking at the ratio of the leading coefficients, because ultimately the ratio of the leading coefficients on our biggest exponent x's is going to be what determines what happens to these functions in the long run. Next one, using the graph of the function, determine a. So we've got 12x cubed plus 5x squared minus 10x plus 8 over 8x cubed plus 2x minus 2. Now, we notice, hey, 3 and 3, and here is a horizontal asymptote. We've got a horizontal asymptote because the degrees are the same. Also, we can see we have a horizontal asymptote in our graph, so it better be the fact that the degree on the numerator and the denominator is the same. So at this point, we know what is our horizontal asymptote. It's y equals 3. We see that by looking at where it goes. It cuts evenly between the 2 and the 4, so it must be at y equals 3. So if that's the case, we know that the ratio of the leading coefficients, 12 over a, right? Leading coefficient on top is 12, on the bottom it's a. So 12 divided by a must be equal to 3, our horizontal asymptote. We work this out, 12 equals 3a, divide by 3, and we get 4 equals a, so a is 4. Great. We've got 28x cubed plus 110x squared minus 47x plus 55 divided by 0.2x to the fourth minus 5x squared plus 4. Is there a horizontal or a slant asymptote? What is it? So in this case, first thing, as always, we look, what are our degrees? Numerator degree is a 3, denominator degree is a 4. So if the denominator degree is larger, it crushes everything, right? It's going to be able to eventually, in the long run, overtake the numerator. It will run faster than the numerator, grow larger, and it will crush everything to 0. So there is a horizontal asymptote, but it's going to be the most boring horizontal asymptote at all, but at the same time, kind of interesting. Y equals 0, right? The denominator crushes that puny numerator. That numerator is just too small, so denominator crush puny numerator because it's got a larger degree. And I want to point out, it seems at first, well, we got 0.2x to the fourth and 28 times x cubed, and there's also these other 110 and other big numbers up here on the top, but on the bottom it all seems like pretty small, plinky numbers. So why is it the bottom's going to be bigger? Because it's got a larger degree. Ultimately, how a polynomial behaves in the long run is really determined by that degree. The coefficients have effects, they affect things, but being really the big dog is just determined by having the biggest degree. X to the fourth, no matter how small that coefficient at the front is, will eventually be able to outrun x cubed, no matter how big its coefficient is at the front. So that x to the fourth will crush the numerator because the numerator only has a degree of 3. All right, final example. So at this point, we've got negative 4x to the fourth plus 7x cubed plus 23x squared minus 43x plus 5 over x cubed minus 5x. We're asked, is there a horizontal or a slant asymptote, and then what is it? First thing we do is we look at our degrees. We've got 4 on the numerator, 3 on the denominator. So that means the degree of the numerator is exactly 1 greater than the denominator. So if it's 1 greater, then that means we've got a slant asymptote, right? And that makes sense because 1 degree larger than something else, if we divide them out, x to the 50th divided by x to the 49th, that's going to become something along the lines of x. So it's going to have a nice linear, it's going to become a line. So that's, degree 1 is a linear function, so that's why we see a slant asymptote, see a line coming out of it. So how do we figure it out? We figure it out by using polynomial division. So x cubed minus 5x, And notice that's 5x to the 1, not 5x squared, so that's going to have a slight effect when we're doing our division. Negative 4x to the 4th plus 7x cubed plus 23x squared minus 43x plus 5. Great. X cubed, how many times does it go into negative 4x to the 4th? It's going to go in negative 4x times, because negative 4x times x cubed gets us negative 4x to the 4th, right? Negative 4x times negative 5x gets us 20x squared, but the next thing we have is 7x cubed. So that's not going to go on the 7x cubed, it's going to go on the 23x squared column. So negative 4x times negative 5x, but gets us 20x squared, so it's 20x squared lines up there. And it's positive. So at this point, we subtract by this amount. So we distribute our negative. That becomes positive. That becomes negative. So negative 4x to the 4th plus 4x to the 4th becomes 0, what it should be when we're doing polynomial division. The first part should always cancel to 0. 23x squared minus 20x squared gets us positive 3x squared. Next step, we bring down the other things that we'll wind up using. So we bring down the 7x cubed. We bring down the minus 43x. So how many times does x cubed go into 7x cubed? It will go in 7 times. 7 times x cubed gets us 7x cubed. 7 on negative 5x gets us negative 35x. We subtract by this amount. So distribute our negative, becomes positive. So 7x cubed minus 7x cubed gets us 0. Negative 43x plus 35x gets us negative 8x. Bring down 3x squared, bring down 5. We've got 3x squared minus 8x plus 5. At this point, can x cubed go into 3x squared? No. X cubed has a larger degree than 3x squared, so we are left with a remainder of 3x squared minus 8x plus 5. So we're left with that remainder. So at this point, we know that our original function, f of x, through division, we've just shown that it's the same thing as negative 4x plus 7 plus the remainder, 3x squared, minus 8x plus 5, divided by our original denominator, x cubed minus 5x. So our answer for what our slant asymptote will wind up being is going to be the part in the front, negative 4x plus 7. That's our slant asymptote. Now we can also check our work at this point by just making sure that if we combine these, we get back to our original function. So let's put them over a common denominator. We have negative 4x plus 7 times x cubed minus 5x over x cubed minus 5x. So what will that wind up being? This is just the same thing here. So negative 4x times x cubed gets us negative 4x to the 4th. Negative 4x minus 5x gets us positive 20x, plus 7 times x cubed gets us 7x cubed. 7 times negative 5x gets us minus 35x, all over x cubed minus 5x, so x cubed minus 5x. And we can add on our thing from our other one, because they're now on common denominator, plus 3x squared minus 8x plus 5. So what's that wind up becoming? We're starting to run out of space, so I'll do this vertically. So we have negative 4x to the 4th right here. So negative 4x to the 4th. Great, that checks out. 20, so next x cubed, 7x cubed. We have no other x cubed, so plus 7x cubed. That checks out. 3x squared, any other x squareds? Oh, whoops, accidentally didn't write the squared. Negative 4x times negative 5x became positive 20x squared. So we've got positive 3x squared, positive 20x squared becomes plus 20x squared. Hey, that checks out. Minus 35x minus 8x, that becomes minus 43x. That checks out. And then plus 5, and that checks out because this whole thing is still over that denominator of x cubed minus 5x. So we've got the exact same thing that we started with. So what we just did checks out. So we know for sure negative 4x plus 7 is good. It's definitely our answer. All right, we'll see you next time when we talk about graphing rational functions in general, being able to use these vertical and horizontal asymptotes together to be able to quickly make the graphs to these kinds of functions. All right, see you at educator.com later. Bye.